Hi, this is Jonathan Dodge, Principal Applications Engineer with United Silicon Carbide. This video is about half-bridge boost converter, and really it's about any of the synchronous rectification DC-DC converters that are in version 2 of FET-Jet Calculator. And in these topologies, both hard switched and soft switch modes, or in other words critical conduction mode, are handled automatically, and we'll take a look at that. So we'll start actually by looking at a simulation. So if we go over to PSIM, I have a boost converter taking 400 volts, converting it to 700 volts, 8 kilowatt load, and I have my half bridge switch on the bottom side, rectifier on the high side, and we'll start off with about 100 microhenry inductor. Run it. Okay, so the top screen is the 700 volts out, a little bit of ripple, actually very small. The next screen down is the inductor current, and here you can see that the current is actually going negative. Okay, and then each switching cycle goes positive and negative, and then of course we have the same thing happening with our switch current and our rectifier current. Okay, so what happens? We'll just use the inductor as a thing that we change here. So let's change to 200 microhenries. So we'll run that. Okay, now if we look at the inductor current and the switch current, we can see we're right on the boundary. Current just goes ever so slightly negative each switching cycle. Okay, and now if we increase it again, we'll go up to 300 microhenries this time. Now we're definitely in a hard switch mode where the inductor current remains continuous, positive, and when the FET turns on, it turns on into a little bit of current. So let's see what happens over in FET-Jet Calculator. So we'll put in the same parameters. So we had 8 kilowatts, 400 volts up to 700 volt, that's the same. We'll start off with 100 microhenries, and we were switching at only 20 kilohertz in that example. Okay, so now if we scroll down just a little bit, we can see in this calculated parameters table that it says conduction mode is ZVS turn on, which means that we have negative inductor current when the switch turns on. That results in 0 voltage turn on the switch, and correspondingly you can see that there is no turn on loss in that switch. Okay, take note of the forward conduction loss. There's a little bit of reverse conduction loss, so the forward and reverse current is taken into account automatically by FET-Jet Calculator when we're in this mode. Okay, so we take a look also at the rectifier. We have significant reverse conduction loss, so this is one of the trade-offs when you're operating this mode. You have low switching loss but high RMS current, which actually United Silicon Carbide FETs are really good at handling. Let's take a look at that real quick before we do anything else. We'll take a look at a larger FET. Let's take a look well, just look at the next bigger one, and then we can see the immediate results. Our conduction loss drops significantly, and our switching loss very, very small. Let's do the same for the rectifier. Let's go really big on this one. 9 milliohm part. Okay, yeah, very low losses. Okay, so that's an advantage of the low on resistant United Silicon Carbide FETs in this continuous, well, I want to say a critical conduction mode operation. So now let's go up to 200 microhenries. Let's see what happens here. Okay, so if we scroll down, we see that we're still in ZVS turn on mode. Our reverse conduction loss really close to 0. So we still have zero voltage turn on switching. We have low losses all over for both the switch and the rectifier. Now if we go up to 300 microhenries, now we're going to be in hard switch mode, and here you'll see the switching losses jump up. Okay, not in the rectifier because it's a synchronous rectifier, but the switch is going to have hard switching. We'll turn on and turn off. So in that case, we might want to go back to a smaller one, smaller FET, a little lower switching loss, and yeah, that's probably a good compromise there. You can see the conduction loss turn on, turn off, and then total loss. As with the other topologies in the chart here, this is per device, and then the temperatures on the right. So again, this is a useful feature in FET-Jet version 2 for the half bridge boost, half bridge buck 3-level synchronous, and boost 3-level synchronous topologies. Hope you find this useful. Thanks for watching.